Получится.
Let us start our last talk before lunch. And after the talk, we will have lunch right here. Yeah. And after that, we will have some something for coffee break also here in that room. Okay, and our last speaker before lunch is Jun Yu from Peking University.
Okay, thanks. I would like to thank you to organize for the invitation, and it makes very great to speak in the workshop. Today I talk about some recent work. Maybe it's in group theory or repeating theory. My title is Brauer tuple with Jacquet-Langlands correspondence. It is a joint work with Professor Jiu-kang Yu in Hong Kong. First, we recall some background. This video is about the so-called Gaussian tuple. So Gaussian tuple is consists of three groups, where G is a finite group, and H1 and H2 are subgroups, and they satisfy the following condition. The condition means that for any conjugate class C in the group G, it requires the number of intersection of H1 and C and H2 and C are equal. If this satisfies, then we say H1 and H2 are Gaussian equivalent, and written as H1 going to H2. So it's clear that the Gaussian equivalent it's a repetition. It means that the repetitions of G act on the functions on the homogeneous space G over H1 and G over H2 are isomorphic. What's the significance of the Gaussian equivalence? So, well, if we take two number fields K1 and K1 and K2, then we say they are arithmetic equivalent if they have the same dedicand set function. And people can we can show that if K1 and K2 are arithmetic equivalent, then they must have the same degree over Q and the same Galois closure. Okay. Then there's the fact that if we have a finite Galois equation R over Q with Galois group G, and take two subgroups H1 and H2, then we have two number fields K1 and K2 from the ADI fixed elements in the field R. Then the theorem said that the fields number fields K1 and K2 are Gaussian equivalent if only if the groups are some number fields are arithmetic equivalent if only if the subgroups are Gaussian equivalent. So we know a number theoretical equation condition is equivalent to a group theory theoretical equivalent condition. Okay. Then now this is the definition for the Brauer pair and Brauer tuple. So for Brauer pair, we actually have quadruple, where G1 and G2 means two. I mean, in application, we took the finite groups, but in our proof, we can extend the definition to profile groups. Okay. And then I and J means two bijections, where I is a bijection. I is a bijection between the conjugation classes, and J is a bijection between the irreducible representations or irreducible characters of G1 and G2. What these two bijection I and J need to satisfy 3 conditions. The first condition just means that to respect the character. Means if when for example when G1 and G2 are finite groups, the first condition just means that the maps I and J give us a bijection between the character tables. Okay, and the second condition is that we require the map I per power map. It means that we take an element X and if I map the conjugate class X to the conjugate class containing Y, so Y is an element in G2. Then the map I should also map the conjugate class containing X power n to Y power n for any integer n. And the third condition that we require the group to be non-isomorphic. So if these 3 conditions are satisfied, then we call G1 and G2 is a Brauer. It's a Brauer. If only the first and second conditions are satisfied, then we call it a weak Brauer. Then a tuple L groups is called a Brauer tuple. If any 2 L, then it's a Brauer. Okay, this is the Brauer and the Brauer tuple. Okay, I mean that's some background. So Richard Brauer is a famous group representing series. In 1963, he asked a series of questions on finite group representing series. One of them concerns the existence of Bruaer. He asked if Bruaer actually exists. Then in 1964, I mean Bruaer's question is solved immediately by Dart, where Dart construct the Bruaer of finite groups of order p power 7. Which have exponent p and near order class 3. Then I mean in maybe about around 20 years ago, some others have more refinement work. So in 2006, the two mathematicians, they showed that it exists a Brauer tuples, which consists of group order p5, p power 5, and then he did some series of work. Control more examples of Brauer and Brauer tuples. Okay. What we do is that I mean as we can see from these 2 slides, the natural construction of Brauer or Brauer tuple are finite p groups. I mean, since for p groups, the structure is simpler and we can it's easier to easier to study the character table and more. Okay. So in our work we use some different completely different idea from representation theory or from by the so-called Jacquet-Langlands correspondence. So these are some techniques used in our work. So first if we have a weak Brauer, which is G1, G2, and IJ, then we can somehow we can have descendant. So if N1 is a normal subgroup of G1 and N2 is a normal subgroup of G2, then we can define some notions. First is that if a character Chi of G1, we say it's a factor through G1 over N1. If the value of Chi at x is equal to Chi at 1, Chi at 1, although Chi at 1 is just the degree of the representation for element x. This can just means if we consider Chi as a representation, that means that representation factor through the quotient group. Then we say that two normal subgroups N1 and N2 are matching. If for any irreducible current Chi, factor through the quotient, if only for the corresponding character J Chi factor through the quotient of N2. If these are satisfied, then one can show that the quotient groups and the corresponding members I bar and J bar also form a Brauer. So this is a descendant property. Then this we use division algebra. Division algebra over the p-adic field QP. So let the p be a prime and n be a positive integer. Then in algebra we know that there is a unique ramified extension of QP of degree n. We write it at E. Then we can form some division algebra of degree n. We write it as dB or dBn. It's a vector space over n. It is the degree sum of En alpha I. So there's a general I, general alpha, where alpha satisfies that condition. Especially the conjugation of alpha on En is given by the base power of the Frobenius. Sigma is the Frobenius automorphism of the field En. And the nth power of alpha is fixed. It's just the parameter p. So you can say that, I mean, for given n, so the field En is given by the number n. But in our construction, the only thing can vary just number b. So we require b to be coparameter n. Then the algebra dBn so compact is a division algebra. And I think this sorry, this should be this is some theorem of Skolem, not Skolem theorem. That such algebra dBn, each dBn is a division algebra over QP, and actually they represent all division algebras over QP. Precisely to say, the map take dBn to B or n gives isomorphism from the Brauer group to Q over P. Q over T. Well, Q over T is Q over T is just it's isomorphic to Brauer. Okay. So such an algebra dBn gives a conquer the realization of all division algebras over QP. Then from this division algebras, we can define some p-adic groups. First, we require for constructing, we require the order number of n to be at least 2. Then we define the set xn is just the number of b, where b is positive and less than n over 2, and and coparameter n. Then for each b, as in the last two slides, we have a divariant algebra db. Then the group db cross db tilde is just the group of immutable elements in the algebra db, and the group gb is the db cross quotient by the center. The center is the scalar matrix. Okay. Then maybe I will recall again in later slides. Then actually the group GB is actually anisotropic. Yes, anisotropic. Our construction is based on the group GB. Okay. Then we recall some properties of the group G tilde B and GB. So for element beta in the G tilde B, so it's just a matrix. It's just a matrix. Its minimal polynomial is a modic polynomial, and we know QP beta, which is actually a fair. The fair general beta over QP is isomorphic to the polynomial in QPX divided quotient by the idea generated by the minimal polynomial. Then this field is an extended field of QP of degree dividing n. Then also we know by the Stockholm knot theory and local class field theory, we know the map from beta to minimum beta gives a bijection from the conjugate class in G tilde B to the set of irreducible monomials over QP of degree dividing n. Okay. Then for the conjugate classes, with the minimal polynomials mentioned in last slide, we can construct a canonical bijection from GB2 conjugate class of G tilde B to conjugate class of G tilde B prime for any two B and B prime. Okay. Since the conjugate class are parameterized by minimal polynomials, when we match minimal polynomials, then we can get a bijection of the conjugate class. Similarly, by descending to the quotient group, then we have a bijection between the conjugate class of GB and G tilde and G prime. Okay. We write this bijection as Sn. Sn means Stockholm knot. Okay. This for on the representation side, we use Jacquet-Langlands. This is a famous theorem. The Jacquet-Langlands correspondence gives a bijection between the representations of irreducible representations of G tilde B and G tilde B prime, and which respect the Stockholm knot map. Okay, this is the Jacquet-Langlands, what Jacquet-Langlands tells us. So, moreover, we know the map JR, the Jacquet-Langlands map. It perceives central character. So then it also induce a bijection of the representation of GB and GB prime, and with their bracket denoted as JR. Then the way the map is SN and KR, we can say that the such group GB form a it should be a so they form a M Bruaer tuple, where the capital N is half of the whole number of n. But but the suggests they are profinite groups, they are infinite groups. But and in the oriented Brauer question, I mean, we needed to consider finite groups. Okay, then our trick is to take that descending. We want to find some normal subgroups to take a descending. Okay, such normal subgroups are constructed via Moy-Persaud filtration. So such groups G tilde B and GB are actually very special. That means that to say that reduce the Bruaer distributing DB or G tilde B is actually a singleton. It's only one point. Then the Moy-Persaud filtration. Then we have the Moy-Persaud filtration associated to the point x0. Okay, the parameter R is a rational number with the denominator n. Okay, and we load the algebra DB as a unique maximum ideal, and we rate it as PD or PBN. Then the Moy-Persaud filtration can be described by the ideal PD. That is the R is a rational number with denominator n, and the numerator I is a non-negative integer. Then G tilde B0 is actually just the OB cross. It's the invisible element in the invisible element in the ring of integers in the Dirac algebra D. Then G tilde B n ION is 1 plus PDI for any positive integer I. Okay, this is the description of the Moy-Persaud filtration. Okay, then one can show that the map Sn it takes the Moy-Persaud filtration of G tilde B to the modifier function of G tilde B prime for any index R. Then for GBR and GB prime R, it is similar. Okay. Then we also noted that the map JR, the Jacquet-Langlands correspondence, it perceives depths both for repetitions of G tilde B and GB. Yeah, and as I remarked in previously, the group GB is n-isotropic. Then n-isotropic. Then any irreducible repetition is finite dimensional, and irreducible repetition pi has depth ION if only if it factors through the quotient by GB I plus 1 ON. Okay, then with the descending method, then we say that then we can show that in the Brauer tuple GB prime, the Moy-Persaud filtration, Moy-Persaud subgroup with index ION are matching subgroups. So I read gamma GBI to be the quotient group. So I can show that the quotient group is the theorem that is quotient group is the Brauer tuple. It's an Brauer tuple. But I think actually the non-trivial thing in the theorem that I mean from what we said in the previous slides, one can show easily that such coaching groups is weak Brauer tuple, but it's difficult to show. I mean, the groups are actually non-isomorphic. The last term. It requires great efforts to show that such coaching groups are non-isomorphic. This is quite non-trivial. But we can show that this finite groups the structure. I mean the structure. I mean they are simple. I mean the structures are clear. I mean for example the order is like this, and below the zero p subgroup is this one, and the zero p subgroup is the norm subgroup, and the zero p subgroup is norm subgroup, and the total coordinate group is the cyclic group. It's cyclic group. Yeah, but anyway, okay. Thank you.
Questions or comments?
Your construction to gives a new example that's not P groups.
Yeah, these are all non-P groups.
Okay.
They are all non-P groups.
And there are ways to go from P groups to more general groups, like there's a construction paths from P groups to more general ones.
From
P groups to more generalized for our couple.
you mean in our consulting or previous consulting?
Previous.
No.
No. Okay. Okay. Thank you.
Okay, let's send this paper again.